Okay, time for the second part. So we saw some example equation solving, and now let's try to summarize and give some types and structure to what we have been doing with this transform. So the general form, the core of it, is that we're saying we introduce a list AS for the coefficients of some function f that we're looking for. And it's the integral of another list of coefficient AS prime. And we know the definition of integ involves zip with. Well, first it inserts f of 0 as the first element, and then it shifts all the elements of AS prime, divides them by increasing integers, and combines that to the output list. And we know that the intention is that AS should be representing f, and AS prime should represent f's derivative. And if we look at what this is doing, we also have a semantic version of this integ. So remember, this integ is working on the syntax, the lists of coefficients, but we also have a corresponding function, I, which works on the semantic side. So the first argument here is the same, it's a real number, but then instead of having a list, the I function takes a function as its second argument. Here I call it g, and then returns a function. So I applied to a starting constant c and a function f, which is then corresponds to AS prime, is the function taking x2 c plus the integral of g from 0 to x. So this integral of a function without any d is not very common in math, so this would be the more traditional form. So it's the constant plus the integral from 0 to x of g of t dt. But as we talked about before, the sort of applying this and then adding dt doesn't add much. The core of it is that the function g is being integrated. And then we add a constant in front. And the laws on the semantic side is that if we integrate whatever constant start the function g and then compute a derivative, we should get back to the g we had. Integration is sort of the inverse of derivative. And this works in both directions. So if you first compute a derivative, then you lose the information about the constant term, but everything else is kept. So if you then integrate starting from that constant term, then you get f back. So this is the interaction of how integration followed with the differentiation, or differentiation followed by integration, is sort of a pair of inverse functions. It's not quite inverses because you have a little bit of loss of information. The constant here is lost, so the g function doesn't know what constant the integral had. And similarly, then when we do it in the opposite direction, we have to supply that information. So one value of f and its derivative is enough to get f back. And the corresponding equations, if we transform, so I was talking here about the transform that I use to solve these equations, and that transform goes from the semantic side to the syntactic side. And wherever it says d here, which remember is something I cannot implement in Haskell, this says deriv, which is something I can implement in Haskell. It's just multiplying coefficients with increasing numbers, and integ, similarly, dividing the coefficients with integers. But otherwise, you see the constant here is kept as a constant. The function g becomes some as, and g in both places is the same as. So the derivative of the integral of starting with the c, the as, then the integral would insert c and shift as and do some division. Deriv will throw away c again and do some multiplication to exactly recover as. And similarly, if I do it the opposite direction, only talking about the sort of lists of coefficients, derivative of f, I said I represent by as prime here after the transform, and f of 0, that's the head, the first element of as. That's the one I would have to put back because I don't know it from the derivative. So I integrate from the head of as, and with this list, then I will get back as. And the reason I put it in a blue box is that this is the equation that we will use for the equation solving, as in this case and in the previous example. So that is syntactic form and the sort of corresponding mathematical laws that we're starting from. So if we now think about a sort of generic example, which we will not solve, but if we had, for example, f prime equals 2 times f, plus 2 times f equals r, where r is a function, and we have the initial condition that f of 0 is some constant z0, then we transform f into as, or rather we hope that there is a list as from which we can get f back, and as prime f prime, and a right hand side list which evaluates the function r. Notice, by the way, that I haven't applied these to x, so this is function plus 2 times a function equals a function. Okay, so the transformation here will say that I want to first express the derivative. So I subtract 2 times f. So the r is transformed to the right hand side, and 2 times f I've written here more strictly as scale to as. So as represents f, and scale will multiply all the coefficients by 2. So then I have an expression computing as prime, and I have the other equation, which is always the same for this transformation, that a function represented by as is the integral from starting at this starting value of its representation of the derivative. So I have two infinite lists, but related by these two equations. And what happens to solve the system, then I have this general pattern that I fill in the first coefficient. I know the right-hand side, that's a function, so I will have to compute the right-hand side's coefficients. So I sort of start with having the first value of as and all the values of the right-hand side. And then the blue arrows here show that from them I can compute using this equation, as prime is the right-hand side minus scale to as, I can compute the value here. And from that first value, so if I just write here and the order, I will get them, not the actual values. The order is, this is the first, this is the second, this is the third, this is the fourth, this is the fifth and sixth value, and so on. So in that fashion, I can fill in by hand or by computer all the coefficients of as, or as many as I have the energy to wait for. I will not solve this one because I haven't specified what r and so on is. So instead we'll go to some familiar examples, the ones I had shown on the first slide of the first part of this lecture. So e of x minus e prime of x equals to 0 with this starting condition. So remember, I should have as the first equation in the pair the derivative in terms how that's related to the right-hand side and the function. So in this case, the derivative is very easily related. If I just shift off the terms here, I can see the derivative is actually equal to the function. And then here I said the function itself is always the integral of its derivative. So that's the second equation, and that's always the same. The only thing which changes here is the 1. The 1 comes from our initial condition. Okay, so now in this particular case, as the first equation is so simple, I don't have to work with two lists as they are the same. So I can just simplify. I insert as, for as prime here, I substitute as. So I just have one equation actually. One equation for an infinite list of coefficients. Okay, so as is integ 1 as. And 1, that's the first thing that's output from as. And then from that one, I can compute by dividing by 1, divided by 2, and so on, the rest of the coefficients. So this would have to be, well, 1 divided by 1 is 1, 1 divided by, so that 1 divided by 1 is 2, well, 2 is half, And then this half is divided by 3 to get the next one. So that's 1 divided by 2 times 3. This is 1 divided by 2 times 3 times 4. And you can guess the pattern here. And clearly, if we then evaluate this function, then the first term is the 1. The second is 1 times x. That's just x. The third is a half times x squared. So that's x squared over 2. And then it's x to the power of 3 over 6, x to the power of 4 over 24, and so on. And actually, I mean, this is, perhaps you've already noticed what function we're after here. This is actually the exponential function. This is e to the power of x. But even without knowing that, it's useful to evaluate it to have the first few coefficients here. It's also worth noting that these coefficients, they shrink pretty quickly. So that means that when you evaluate this one, we can stop after a while because the coefficients will become very, very small. So that means that we can approximate the true power e to the power of x function by a finite prefix. Because, for example, if you have double precision floating point numbers in the computer, after a while you will not be able to change the last bit. And there is no point computing after you can't change the number anymore. Okay, so this was solving the first example. Yeah, and this I'd pre-written and noticed also that it would be 1 over factorial of n at the nth term. Let's take one more classical example. So this was also from the first slide. I was saying, let's look for a function s such that if we add the second derivative, then we should get 0. So they should be completely opposite at each point x. And here we need it as it's a second order ODE. We also need 2 starting conditions. S0 of 0 and S prime of 0 is 1. Okay, and now let's see, we should use this pattern that we take the highest order derivative. In this case, that's AS double prime. S prime is transformed to AS double prime. We should express that in terms of the right-hand side and the other terms. In this case, it's just minus AS. Just move this over to the other side. And then all the other equations, in this case 2 of them, just show that the first derivative is the integral of the second derivative, and the function itself is the integral of the first derivative. And, well, we have to integrate from a starting condition, and that's the 1 we get from here, and the 0 we got from there. Okay, and if we want to start filling this in, we can start by filling in the information we know from the integ. So, for example, at the very bottom, we have a 0. And then we got, for AS prime, we got a 1. And then from these 2 and this equation, or actually just from the below 1 and this equation, we get this bottom. So this is minus 0, if we would like. Well, I'll just write minus 0, the same as 0. And now the red little arrows indicate that I can try to move diagonally downwards. And what I mean with diagonally downwards here is using the integ equations. So let's underline them by red. Remember, that was the zip width division and the increasing powers. So, for example, if we take this one, this definition using AS prime to compute AS. So we want to compute the AS first component, and that comes from the 0th component of AS prime. So that's just 1 divided by 1, which is 1. Similarly, we can use this equation to compute the next term of AS prime using the first or the 0th term of AS double prime. So the minus 0 here divides by 1. Well, 0 becomes 0. So, well, I could write minus 0, but I keep it 0. And then actually we can move even one more step, because the 0 here will give us 0 divided by 2, which is just 0 down here. So at this stage, we sort of filled in one round of this, and we've already approximated the function that AS represents, the function S, by not only zeros and first, but second order terms. So it's, I mean, somewhere down here we can say that S of x is approximately 0 plus x plus, well, no x squared, 0x squared plus, and so on. So let's at least fill in one more. I think actually I did that on the next slide. So this is following on. So what I'm doing after I have moved diagonally downwards is I use the top equation again. So in this case, the 1 here becomes minus 1. And then I have to divide by 2. So I put down here a reminder where I am in the sequence. Position 0, 1, 2, 3, 4, and so on. So when I move up to that, I should divide by that number. So for example, here it's minus 1/2. And here it becomes then minus 1/6. I divide if I move diagonally one more step. And I already pre-written that and a few more steps. As you can imagine, I can fill this in step by step, and I will get this nice pattern of every second diagonal are only zeros, and the rest will be a number which then divides down and continues. And this is now summed up here. So S of x, which is the eval of AS of x, is approximately, well, it's 1 times x. There's no x squared. It's minus x3 divided by 6, no x4 term, and it's x5 over 120. So this is actually the 5th order approximation of the sine function, because the s here is actually the sine. So this is sinus of x in radians. So as you can see, the way of filling in these equations in is rather standard as long as you got the equations right. And the equations, well, if you start from here, the transformation is to get the highest order term in terms of the rest, and then the lower order terms and the function itself are just integers. And all of those would mean dividing by whole numbers. So you can sort of turn the crank, compute the terms, and get an approximation of the solution. And sometimes you can also see the pattern and get a general equation out of it. Okay, that was all for this part.